Hello everyone, this is the Space Debris Team, also known as Project Sigma. My name is Ruhaan Singh and I'm from Knoxville, Tennessee.
My name is Aditi Muduganti and I'm from Onalaska, Wisconsin.
Hello, my name is Aliana and I'm from Fall River, Massachusetts.
Hi, I'm Ricardo and I'm from Mission, Texas.
Hi, my name is Garrett Lee and I'm from Overland Park, Kansas.
Hi, I'm Jahstone and I'm from Chicago, Illinois.
The goal of Project Shooting Interplanetary Garbage, Material Ablation, or SIGMA for short, is to reduce the amount of space debris in Earth's orbit, thus decreasing the dangers for satellite and other spacecraft. A UV laser in low Earth orbit targets and ablates debris between 1 centimeter and 10 centimeters. This ablation causes the object to decelerate, reducing its orbital lifespan and incinerating it in Earth's atmosphere sooner.
But what is space debris? According to NASA, it's any human-made object in orbit about the Earth that no longer serves any useful purpose. This includes derelict boosters and even paint flicks. And since this debris is moving at thousands of miles per hour, any collision can cause massive damage. As more spacecraft are launched into space, the risk of collision increases. Just this past June, a Russian satellite exploded, sending even more space debris into Earth's orbit and forcing astronauts on the ISS to shelter. Monolithic aluminum blocks are used in spacecraft for their lightweight design, but can be penetrated by space debris at the high velocity they travel at, with many traveling at 10 kilometers per second or faster.
Currently, 4 areas of space debris research are being tackled: detection, tracking, characterization, and solutions. Additionally, there are 2 different types of solutions: mitigation and remediation. Mitigation strategies involve preventing, avoiding, or protecting against space debris, while remediation focuses on actively moving the debris. However, most research doesn't cover remediation. Tracking is a main focus for space agencies globally. However, debris smaller than 1 centimeter is currently unable to be tracked, and improved radar detection is required. Though, if satellites are on course to collide with known debris, the satellites will be directed to move out of the way. Another recommended mitigation strategy, PMD, is a preventative measure for spacecraft nearing the end of their service time, forcing them to lower their orbits, thus reducing their risk for damage and to become space debris. Shielding was also mentioned, with multi-layer hybrid walls being used to lessen the damage incurred by collision with debris. For the last of the mitigation strategies, scientists looked at passive methods, primarily reducing the risk of spacecraft explosions via batteries and fuel, thus preventing space debris from forming. In comparison with remediation strategies for cost, it was concluded that remediation is just as effective as mitigation in both short-term outlooks and should be planned for in the long time.
We looked at many different remediation techniques, including a space net and magnetic tethers. However, laser ablation had the highest reduction rate, tied with the ground-based laser, as well as being the cheapest at a total cost of $500,000 per kilogram of debris removed. This made it very easy to settle on ablation using space lasers as our method for deorbiting the debris in this research.
Ablation works through laser irradiation. When the laser is fired, part of the debris material is vaporized, changing the momentum of the debris and sending it back into the atmosphere. The amount of space debris doesn't increase with ablation, and it provides powerful enough pushes to reduce the lifespan of debris by years. However, since it's more powerful, it requires more energy and precision.
First, we looked at the French proposal for a space laser mounted on a satellite. Such a space laser would be effective at deorbiting both large and small debris, and be more affordable for each piece of debris removed. But there would be a high cost to launch and repair the satellites. Another proposal included solar panels and a mirror to target the laser, making it more precise. However, altitude differences would affect the laser's performance, and the mirror would make the spacecraft more fragile.
Overall, our proposal would provide a solution to eliminating 1 to 10 centimeter space debris using remediation. It would require a satellite sturdy enough to house a laser system, solar panels for power, and control mechanisms including stability systems to maintain its orientation, an arm for maximum freedom and accuracy, and a lens to increase preciseness would also be needed. A tracking system would be used to track debris in real time and continue predicting the trajectory of the particles. The minimum success would be a satellite capable of identifying debris and vaporizing its surface to deorbit it, with the altitude of interest being between 200 kilometers and 2,000.
The cube-shaped satellite would hold foldable, multi-junction solar panels on both sides. The excimer laser would be mounted on NASA's robotic servicing arm, which would be placed on top of the satellite. Sensors, radar, and cameras would track debris, while an algorithm working in conjunction with existing European Space Agency models would calculate the angles for when and where to fire the laser as both the satellite and debris orbit the Earth. A high-capacity battery would power the whole system. The satellite would be launched into low Earth orbit with a polar elliptical orbit to maximize the field of view the laser could fire at.
Materials for the satellite include a framework, which would be stainless steel, titanium, and lightweight aluminum, similar to other satellites of this size, minimizing weight while not sacrificing structural integrity. Furthermore, a large lithium-ion battery, minimum 100 V, would be required to power the satellite systems and power the laser pulses. This would be powered by the large solar arrays of the craft, located on your bottom left. At minimum, 6 2x3 meter multi-junction and solar panels would be required to keep the systems online. Lastly, the krypton fluoride UV laser mounted on a motorized robotic arm would be required. The full system would cost around $700 million, but could cost up to $1 billion.
Our design features three main instruments and systems. The laser, attached to NASA's robotic servicing arm, or a similar device, has 7 degrees of freedom, which allows for unrestricted field of view for laser firing, only confined by the laser's range. This mechanism will be mounted to the top of the 2 meter by 2 meter by 2 meter cubic satellite. On the two opposing sides, foldable multi-junction solar panel arrays will be mounted to provide a constant source of energy to charge and power the spacecraft. Thirdly, the satellite will have a radar device to identify and track space debris from its location, allowing it to hone in on specific debris.
NASA's robotic servicing arm has a high range of motion with 7 degrees of freedom, allowing it to perform a wide range of tasks in space, including maintenance and payload handling. It also has mechanical joints that provide precise control and manipulation capabilities. Its precision makes it perfect to hold the laser. In this picture, the arm is shown extending from the space shuttle, known as the Canadarm, to position the Hubble Space Telescope during a servicing mission.
The laser itself would fire short, powerful, 248 nanometer ultraviolet pulses at space debris. This causes ablation by vaporizing material from its surface, which creates thrust that slows the debris down. The reduction in velocity accelerates the debris, causing it to re-enter Earth's atmosphere and burn up quickly. The specific UV laser chosen for the satellite is a krypton fluoride laser. Through a pulsed power supply and a chamber of krypton and fluorine, the gases form an excited krypton fluoride molecule. As it decays to a stable, unexcited state, the molecules release energy in the form of a UV wavelength at 248 nanometers. This is represented by the equation shown at the bottom of the photo. Mirrors in an optical cavity increase the amount and intensity of UV light emitted. To reduce divergence or beam spread, a convex lens collimates the laser beam by bending light rays to make them parallel. This improves the precision of the laser, making it better at targeting space debris.
In order to ensure a space laser would work, calculations must be done to ensure its effectiveness. First, we must guarantee that the ablation threshold of aluminum is reached in order to actually impact the debris. The approximated fluorescence, around 100 joules per centimeter squared, is much higher than the minimum threshold of around 10 joules per centimeter squared of aluminum. Next, from the mass removal calculations and impulse calculations, we can approximate how much we can actually slow down the debris by per laser pulse. As you can see, the velocity of the space debris can be altered by roughly 0.4 millimeters per second for every pulse of laser light shot through the laser. This would equate to a change of 0.4 centimeters in its velocity every second, and this amount is significant to the point where the ablation technique by using space lasers is a viable remediation strategy.
In practice, the satellite will use its radar to locate space debris in low Earth orbit, which ranges from 200 kilometers to 20,000 kilometers. Once the radar completes the data collection, it fires the UV lasers towards the target. The satellite will turn off when it either completely removes space debris from LEO or becomes inoperative.
So we used Python's matplotlib and NumPy libraries to simulate a two-dimensional model of orbital debris. Each particle was given a randomly initialized orbital velocity and position orbiting the Earth. The blue sphere represents the satellite, and the red particles represent space debris. The laser was represented by a line connecting the satellite and the targeted debris, and the D-orbit was shown with the debris disappearing. Additionally, the algorithm draws the angle and distance required for the laser to hit the particle and ensures that when the distance between the debris and satellite is too high, the laser does not end up being fired.
Before deployment, there need to be existing agreements and cooperation between global organizations such as the Space Surveillance Network, European Space Agency, Federal Communications Commission, Federal Aviation Administration, and the National Oceanic and Atmospheric Administration. Additionally, funding would be required to launch the satellite, and we'd have to ensure the laser wouldn't target or accidentally fire at currently operating satellites. This would require safety protocols and real-time monitoring.
Once the satellite has been deployed, the continuing removal of space debris will be less expensive in comparison to the upfront launch. The life expectancy of targeted debris would be reduced, and once the debris entered the atmosphere, it would burn up completely due to its smaller size. There would be no risk of the debris impacting populated areas.
Ultimately, the Sigma satellite proposal would be the most cost-effective option for a remedial solution. It would reduce the amount of space debris between 1 and 10 centimeters in low Earth orbit by using ultraviolet light to ablate the debris. The project ensures that the debris is incinerated upon entry into the atmosphere.
In the future, extensive testing both on the ground and in space would be performed to validate the effectiveness of UV lasers in different operational conditions and refine the technology based on test results. This would be applied to make the excimer laser as energy efficient as possible. Additionally, different methods to target the laser would be studied. Aside from existing technologies such as a mirror, an internal gyroscopic mechanism would be evaluated where gears could be shifted in order to change the momentum and angle of the satellite. This would let the laser be affixed to the satellite and allow it to still be targeted when the full system rotates. As more space debris enters orbit, our proposal will continue to be modified and improved.
Thank you guys for watching. We'd also like to thank Ms. Tomlin, Ms. Baggio, and Ms. Miller for their expertise, as well as the helpful mentors of Jimmy Barker and Mauro Esquivel. Additionally, Doug Frank from NASA was a great help, and Mariba Jah was a great inspiration.
My experience in the SEAS program were unexpected and significant. At first, I felt nervous about being grouped with complete strangers from around the United States. But as time passed, I was able to connect more with my teammates. Eventually, I considered them good friends, and them and I were able to complete our projects and learn more about space science.
My participation in the NASA SEAS summer internship was an amazing experience. From iFly to late nights researching, I had a blast throughout the entire week. I was fortunate enough to meet such an amazing group of people, including my teammates and mentors, who all made this experience such a wonderful one.
My engagement in the SEAS program will have a lasting impact on me, from exploring future paths in space science to making new friends. After touring the NASA Johnson Space Center and flying at iFly, I have been able to have amazing experiences with my teammates. Me and my team were able to work together and brainstorm our project, which deepened our friendship.
Being a part of the Space Debris Solution team on the SEES internship program has left a lasting positive impression on me. I met some really cool people, and my teammates have become family to me. Although the early mornings were quite rough, I truly enjoyed all the exciting places we visited, like iFly and the JSC. And working together to brainstorm experiments and work through problems was enjoyable with the help of my teammates. I'm truly grateful for my time at SEES.
Being a SEAS intern was impactful and a growing experience. At first, I was nervous and uptight, but as soon as I met my group, we all clicked, and as the days passed, we grew closer. This experience had me learn different ideas and perspectives in multiple genres, and I will be forever grateful for it.
As for me, I made some of my greatest friends at NASA SEAS, and I will be forever grateful to this experience for letting me make those friends. I also was able to connect with many NASA mentors and grow my worldview as well as my connections with others. Additionally, during the evenings when we weren't working on this very presentation, we also played pool, and it was really cool to make those connections between the research we were doing and the trajectory at which the cue ball had to be fired into the rest of the balls to make sure they went into the hole. I will never forget my time here, and I will cherish all the opportunities that come of this research. At this time, we are now open to questions. Please submit them through the Slido.